Hi, today we will talk about what do we need these different types of convergence for. So we need them to understand the limit theorems of probability theory. Actually, this is a batch of theorems that are collectively called the limit theorems. And the first one is the law of large numbers. The law of large numbers also is not just a single theorem. It is also a set of theorems that are similar to each other, but a little bit different. But I'll give you just only one of them, so only one variant of the law of large numbers, that is called the LLN for identically distributed random variables. Why? Because this variant is the most often used in practice. So why? Because its conditions can be easily checked. So for the other variants of the LLN, it is sometimes difficult to understand, are the conditions of the theorem met or not? And here it is usually easy. So what is the theorem? If you have a random sequence, so a sequence of random variables, x1, x3, x2, x3, and so on, and they are independent and identically distributed, and they have a finite expected value, so as they are identically distributed, so they have the same distribution, that means that all numerical features are also the same. The expected value also is the same. So E of x1 is equal to E of x2 and so on. And so the condition is that this expected value must be a finite number. So it cannot be equal to infinity. So, and the xn bar is the arithmetical mean of the first n elements of this sequence. So x1 plus x2 plus x3 up to xn divided by n. Arithmetical mean. So if it is so, then when n tends to infinity, xn bar converges in probability to mu, to the expected value of xi's. So how this can be understood? So let me give you a little example. Let's imagine that you have a table and you want to measure the length of this table, but you have no measuring tape. And that is why you have only a short ruler, and you're going to measure the length of this table by attaching this short ruler several times. And you see that such a measurement is not so very accurate. It gives you an error of approximately 5 millimeters, and you want to measure the length more accurate. So what can you do? Obviously, our intuition tells us that you can measure the table length several times and then calculate the arithmetical mean of these measurements. So, for example, you do these 10 times and then you calculate the arithmetical mean. And we know that if we do so, the result of this operation, so this arithmetical mean, is more accurate, more close to the real length than any of the single measurements. So when we are doing so, we are applying the law of large numbers in practice. So we say that the result of each single measurement is a random variable that is element of this sequence. So x1 is the result of the first measurement, x2 is the result of the second measurement, and so on. And then, the way of measuring is the same each time, then they are all identically distributed. So the result of each measurement is a real length of the table plus the random error, so measuring error. And so as they are all identically distributed, and we assume that there is no systematic error, so that this length is never underestimated or overestimated systematically, then we can say that the expected value of each single measurement is the real length of the table. So the real length, what we are looking for, is the expected value of all these random variables. And so then, according to this theorem, as they are independent and identically distributed, and they have the same finite expected value, when we calculate the arithmetical mean of all measurements, it will converge to the mu, to the mean value we are looking for. So the more is the number of experiments, the more close this x bar is to what we are looking for, to the real length of the table. The second theorem of our interest for today is the central limit theorem, or the CLT. It is also not a single theorem, but a set of several theorems, and I also give you only one of them that is applied in practice most often. The CLT for identically distributed random variables. So you see that here conditions are similar to the conditions that we have already seen in the law of large numbers. So we have a sequence of random variables, and they must be independent and identically distributed. Actually, in mathematical statistics, we often deal with such a situation. We often assume that what we are observing are independent and identically distributed random variables. Often the abbreviation IID is used for this. IID means independent and identically distributed. So, and here they say that not only the expected value, but the variance of the elements of our sequence also is to be finite. And now we are dealing not with the arithmetical mean, but with the sum of the first n elements of our sequence. So yn is x1 plus x2 and so on up to xn. Sum of the first n elements of the sequence. And so the theorem states that if it is so, then y, when it is centered and normed, so this operation, when we subtract the expected value of a random variable from this random variable, is called centralization. So we can say that yn minus e of yn. While doing so, we are centering this random variable, and by dividing it by the square root of its variance, we are norming it. So centralized and normed y tends to a normally distributed random variable when n tends to infinity. So when n tends to infinity, this random variable that we see in the left part of this formula converges in distribution to a random variable that has standard normal distribution. Standard normal means normal with parameters 0 and 1. So how this can be applied to our real life, to the calculations we are doing sometimes. So this means that if n is big enough, then we can assume that y is normally distributed with parameters e of y and variance of y. So in practice, this theorem means for us that if n is big enough, then we can assume that the distribution of y is normal. So no matter what the distribution of x's is, so x's can have any distribution. Uniform, binomial, geometric, exponential, Poisson, or some unknown distribution. So x can have any distribution, but their sum, if they are independent and identically distributed, their sum, the distribution of their sum, will be getting closer and closer to the normal distribution when n is growing. So when n tends to infinity. This theorem is a very interesting one. I would say extremely interesting, because it is at the same time the mathematical theorem and the physical law. Usually we deal either with mathematical theorems. So what does it mean? It means that mathematicians introduced some objects, they define them. So they say, let us call a function this thing, and let us call the derivative this thing, and let us call the function being differentiable if these conditions are met, and so on. And then, using these definitions, they introduce themselves, they prove theorems. So that is how this is usually done in mathematics. And in physics, they don't have theorems, they don't have definitions, they just observe real life, they do experiments, and so as a result of these experiments, they can find a physical law. So they can say that let x, y, and z be some measurable physical variables. And so we have found that this formula is true, that x is equal to, let's say, y divided by z. So, and they do not prove this anyhow. They say, you can just check. So you can repeat our experiments and you will see that this formula is true. So physical laws are not proved. They are just checked by doing some experiments. And the central limit theorem is a mathematical theorem and a physical law at the same time. So it can be proved as a mathematical theorem. So this statement that you see now can be proved as we do in mathematics. And from the other hand, you can just check that it is true by experimenting. So you can observe some random variables and that are such that these conditions are fulfilled, so that are independent and identically distributed, and you can add them, and then you can see that really this theorem is true. So the distribution of sum is getting closer and closer to normal one, to the normal distribution. So you can deal with this like with a physical law. That is why it is very interesting. Let us see how the central limit theorem can be applied to calculate different probabilities. So let's assume that the step length of a certain person, is a random variable that has uniform distribution, continuous uniform distribution. So let's say that x is the step length, and so it is random, and its distribution is uniform, let's say from 0.7 to 0.9 centimeters. So here we assume that length of a step, of a random step, can take any value from this range, from 0.7 to 0.9, so from 70 to 90 centimeters. So, and that it can equally likely can take any value from this range. Actually, this is not true. Actually, step length is not uniform distributed, but still let us assume that it is so, just for our example. And the question is, what is the probability that this person will walk a distance of at least 85 meters in 100 steps? So that after walking, he will make 100 steps, the distance he will walk will be more than 85 meters. So here we should, to deal with this, we should modify our notation a little bit. We should say that we have 100 steps, and each of them is a random variable. So xi is the length of the ith step, and I is from 1 to 100. So, and the distance he will walk after 100 steps is the sum of these x's. So, y is the distance after 100 steps, and this y is the sum of x's. Y is x1 plus x2 plus x100. And let us also assume that these lengths of this person's steps are independent. So let's assume that they are independent. This is also not 100% true. So that if we know that the length of a given step was a short one, so the probability that neighbor steps are also short increases. Maybe that means that he's walking carefully, and so because of this his steps are short. So, but still, let us assume this. And so after we say that these xi's are independent, and after we say that they are all identically distributed, we can say that we can apply the CLT. So that their sum is subject to the central limit theorem, and the 100 is big enough to apply the CLT. So we can say that n, that is equal to 100 in our case, is big enough to say that according to the central limit theorem, we can assume that sum of our x's, so that the y is normally distributed. So that y has normal distribution with parameters e of y and variance of y that are yet to be found. So let's now find them. We know that as xi follows the uniform distribution from 0.7 to 0.9, then expected value of xi is 0.7 plus 0.9 divided by 2. So this is the middle point of this interval. This is 0.8. And as for the variance, we can say that we also know the formula of the variance of a uniformly distributed random variable, and it is 0.9 minus 0.7 squared over 12. And this is approximately 0.03. So these are E of x and variance of x. And so as y is the sum of x's, then we can say that so E of y is E of the and we know that expected value of a sum is equal to the sum of expected values. So this is equal to E of x1 plus E of xn. And so all these expected values are the same, and they are equal to 0.8. And so we have not n, but 100 here. So 100, so this is just 0.7 multiplied by 100, that is 80. So expected value of y is 80. And the same is true for the variance. So variance of y is variance of sum of x's. As we know, variance of a sum is not always equal to the sum of variances, but it is equal if x's are, if these random variables are independent, if they are uncorrelated. So if covariance is 0, then variance of a sum is equal to the sum of variances, and this is our case as x's are independent. Independent means that also they are uncorrelated, means that covariances are zeros, and that variance of a sum is equal to the sum of variances. And so this is 0.03 times 100, and this is approximately 3. So we can now assume that y has normal distribution with parameters 80 and 3. So now we can say that we can assume that distribution of y is normal with parameters 80 and 3. And let me remind you what we are going to find. So we were asked to find probability that this person will walk a distance of 85 meters or more in 100 steps. So this is mathematically, this is probability that y is more than 85. So we need to find this probability, and we can do this as the distribution is assumed to be normal using the phi function. So probability that y is more than 85 is 1 minus probability that y is less or equal than 85, and this is 1 minus the CDF of 85, and as y follows normal distribution, the CDF can be expressed as phi of 85 minus mu, that is 80, divided by the square root of the variance, that is 3. So this is approximately 2.88. So this is 5 divided by square root of 3. This is approximately 2.88. And the value of phi in this point is 0.998. So almost 1. So if we subtract what we get, we will get 0.002. So we see that theoretically, as maximal possible value of each step is 0.9 meters, so it's 90 centimeters. That means that theoretically, in 100 steps, this person can walk 90 meters. This is possible if each step will be equal to the maximal possible value. But we see that even probability that y is more than 85, so probability that he will walk more than 85 meters in 100 steps is almost 0. It's very close to 0. So if we assume the uniform distribution for the length, for the step length, it's almost impossible. Such a situation that lengths of many steps, of so many steps, being more than average, so this situation is almost impossible for such a distribution of the step length.